All right, let's begin talking about linear regression. And to kick things off, let's begin by talking about the linear correlation coefficient. This thing is R, has the little symbol R. But we'll get to that in just a few minutes. First, let's talk about z-scores, or standardized values of observations. Okay, the z-score, or standardized value of an observation x, is just the number of standard deviations it lies from its mean, and also it tells you the direction that it lies from the mean. So, for example, maybe you have a data set, and I'll make a easy little dot plot that looks something like this, okay? And it's probably not too hard to believe that the mean is, say, right there, okay? Then the z-score for this data value is the number of standard deviations that it lies from the mean and in what direction, okay? It's captured by this formula right here. And the z-score for this data point will be the number of standard deviations that it lies from the mean and in what direction. So you can see just by inspection that this data point should have a negative z-score, okay? Falls a little to the left of the mean. Okay, this point should have a positive z-score, and it should be larger in magnitude than the z-score for this value. Okay, and again, you can tell just by looking at the formulas that that's exactly what the z-score captures. It's the number of standard deviations that that it lies, and in what direction from the mean. We can talk about these standardized values with respect to populations and also for samples. If we talk about these things for distributions or populations, then we'll be using the population mean or the distribution mean, and the population standard deviation or the distribution standard deviation. Okay. On the other hand, if we're talking about a data set, then we'll use the sample mean for the mean, and we'll use the sample standard deviation for the standard deviation. Remember that the difference here is S is the sample standard deviation is typically these days defined to be, it's the square root of the sum of squared deviations from the sample mean divided by n minus 1 down there, okay? N minus 1 so-called degrees of freedom. The reason for this, and we'll see this later on in the homework, in fact, is that the stuff under the radical sign is actually an unbiased estimator, is the deal. It's an unbiased estimator for the actual population variance, okay? But, and similarly, this sigma here, the population standard deviation, is, remember, that's defined to be, it's essentially the same formula, right? Except you take all the values in the population if it's a countable population there. Take the square deviations from the mean and divide by the total number in the population, big N. Okay, so here's some facts about z-scores. It turns out the mean is always 0. The mean of the z-scores is always 0, and the standard deviation is always 1. Here's the idea. Okay, if here's 0 down here, and here's x bar up here. Maybe I have a data set. Think of this stuff in terms of data. Maybe the standard deviation here is something like this much. Okay, so if I standardize these points, what happens is the whole operation, it shifts the point pattern down so that it straddles 0, and then rescales it by the standard deviation so that the new standard deviation is 1. That's effectively, in fact, exactly what happens. Okay, we'll see this over and over again. So, the deal is that it might shift this way. If the sample mean is positive, greater than 0, then by standardizing these data points, they just shift down here so that they straddle 0. The new mean is 0, and the new standard deviation is 1. Now, I'm not going to prove number 2. I'll leave that to you. Whoops, sorry. I'll leave that to you for a homework exercise. But to get you running in the same spirit, I'll prove number 1 here real quick. So we want to show that the mean of the z-scores is always 0. Well, the mean of the z-scores you could express like this, right? Okay. It's the sum of all the z-scores divided by the number of them. Okay, and so let me just write. Let's see, what is a z-score? It's the ith value there. Let me think in terms of data. Okay, maybe so I'll subtract the sample mean divided by the sample standard deviation there, and I'll pull the sample standard deviation outside the summation there because you can just factor 1 over s out. You get 1 over ns times the sum, right? Xi minus x bar. Okay. And in fact, okay, now maybe I could just could I do it like this? All right. You see that? I'm just going to sum over the xi's and then sum over the x bars. Whoops. There we go. And now then, what does that become here? Well, let's see. You know what? If I take the sum of these xi's and divide by n, hey, that is the sample mean, isn't it? So this first part is x bar over s, and then minus. Okay, here I'm summing up a bunch of sample means. How many am I summing? Well, remember, I really goes from 1 to n here over all the sample points. So I'm summing up n of these sample means. So this is minus 1 over ns times n sample means. The n's cancel, and I just get x bar over s minus x bar over s, which is equal to 0. Okay. All right. In a similar spirit, you can. And it takes a little bit longer, but you can show that the standard deviation is always 1. I want you to do that for homework. Okay, number 3 here. So if the data distribution is mound-shaped, or if you're talking about instead of data, if you're talking about a population, if you have a mound-shaped distribution, then the empirical rule, or by the normal probability distribution, normal probabilities. The empirical rule says that about 68.27% of the observations will fall between will have z-scores between -1 and 1, and about 95.45% of the observations fall between -2 and 2, that is, of the z-scores, and about 99.73% of the z-scores fall between -3 and 3. Okay, it's equivalent to saying that 68.27% fall within 1 standard deviation of the sample mean, or 95.45% fall within 2 standard deviations of the sample mean, and so forth. So this is, once you standardize the data, you got about 68.27% fall in there. Okay. And here's 1 to 2. About 95.45% fall in there. Maybe I'll shade that a little bit. Okay. And then finally, about about 99.73% fall within 3 standard deviations of the mean, or after you standardize it, between -3 and 3. Okay? That's the empirical rule. All right. The linear correlation coefficient, R, measures the magnitude and the direction of linear association between 2 variables, and is defined to be all this junk. Okay. Now let's see if we can make these expressions make some sense. Here's the idea. Here's what's going on. Okay. Let's say you have a data point pattern. Okay, and for whatever reason, this point pattern maybe sort of looks like this. You've got x variable and a y variable. Okay. two variables here. This course on regression is largely about how multiple variables play along with each other. And right now we're just considering two variables. We can think of this as the x variable is a predictor variable or explanatory variable or independent variable. And this y variable is a response variable. It's a variable that sort of responds to the x variable, okay? Or sometimes it's called a dependent variable. All right, so let's see. Where's the center of this random point pattern? Maybe it's right there. Maybe this is the center mass, x bar, y bar. Okay. Well, it turns out, let's draw a new set of axes running right through var. Okay. So look at what you have here. It looks like the trend of these points is sort of going from upper left to lower right, right? So I would guess that there is, maybe you could say that there's a negative association here between these two variables, because as one variable increases, the other variable decreases. Or similarly, as one variable decreases, the other one increases. Another way to say that is that above average observations of the x variable tend to occur with below average observations of the y variable. Here are my average lines, okay? And that's indeed the case. Not necessarily always the case, but it is sort of the trend, right? Below average observations of another variable tend to correspond with above average observations of the other one, okay? So now what we'd like to do is somehow wrap all of that stuff up into one number. And this R guy, it's called the linear correlation coefficient, is a good attempt at that. Okay, look at this formula here. What are you doing? You're finding, first of all, you find the z-scores for the x values and the z-scores for the y values and multiplying them and summing them up. So let's take a look at this one right here. Okay. If this one, in fact, all of the points down here in this region will have all these points down here will have above average observations in the x direction and below average observations in the y, right? So they'll have positive z-scores in the x direction and negative z-scores in the y direction. Similarly, up here, but differently, these points will have negative z-score values in the x direction because they sit below average in the x direction and above average values in the y direction. So they'll have negative x z-scores and positive z-scores or standardized scores in the up-down direction. And these points will have positive z-scores in both directions, and negative z-scores in both directions occur for points down in this region, like this point right here. Okay. So now look at what the formula does. It essentially, I mean, if this -1 wasn't here, it would simply be an average of the products of the z-scores. So that is, you know, for this point it would take a plus times a minus. And this point it would take a plus times a minus. And for this point it would take a positive times a positive. Here you have a negative times a negative. You have, it looks like from this picture, it looks like you have mostly a bunch of numbers with opposing signs. You have a couple where they have the same sign, but for the most part it looks like you have a bunch of products you're summing up a bunch of negative numbers, right? The end result is you have 1, 2, 3, 4, 5 products with negative signs and a couple of products with positive signs. But these two products are going to be the result from the multiplication of those z-scores are going to be, you know, pretty close in. They won't be as large in magnitude as these are because these are sort of farther away from the center point there, right? So in this case, I bet R is going to be below 0, don't you think? Yeah, because the average, this is essentially the average of a bunch of mostly negative things. And the average of a bunch of mostly negative things is probably, it's kind of likely to be negative. On the other hand, if I had a picture that looked like this, okay, what if I had sort of a positive trend, okay, like this. Well, the center of mass for this kind of point pattern is probably right at about there. And so if I redraw these axes, which is sort of like centering my data, right, I'll have, again, points down here. We'll have opposite sign z-scores for the x and y z-scores. The points up in this region up here will have negative x z-scores and positive y ones, and then you have plus plus here and minus minus here. And what do you have in this case? You're going to have a bunch of positive products contributed from these points, and positive products contributed from these points, and then you have 1, 2, 3 negative products, because these have opposing signs for their z-scores, but they're kind of close in. So probably my guess in this case is that R is going to be positive. Okay. What do you think? Okay. One more comment I want to make is that it turns out that R is always some number between -1 and 1. This is something that you can prove. We won't, but it's true. And the closer that R is to +1, the more straight on a line the data points look. Okay, the more if R is close to -1, the more straight on a line they look this way, but with a negative slope. Okay, the closer R is to 0, the more uncorrelated the points are going to look. Okay. Okay. There's no real magic, lines of demarcation here. Is an R value of 0.95. Does that indicate a strong positive association? Yeah, probably. So does an R value of 0.75. What about 0.74? Well, I don't know. It's just smaller. Okay, an R value of -0.8 that sort of indicates a strong negative association. Okay, an R value of -0.05 is a very weak, almost no, maybe a very, very weak negative association. But so that's the deal.